Okay, I suggest that we just get started, and welcome back everybody, for those both here and online. So the topic today is essentially a continuation of what we did on Monday. And what we are going to do now is to, we are going to try to derive the equations of motion, and we're going to look at examples as well. And one of the examples which we're going to look at is the harmonic oscillator, 2 dimensions, because that is also going to give us some insights about how we can interpret these equations. And what is coming now is, again, a set of small tricks, and which will allow us to solve analytically the equation of motion in this relative coordinate degrees of freedom. So let's just go through the gritty-nitty details. Let me also quickly remind you of the plans for the rest of the week. So on Friday, we're obviously going to look at exercises. And today is an attempt to get at the final equation of motions and how we can solve them and what the solution is going to look like. And I wanted also to digress into the harmonic oscillator in 2 dimensions. So to quickly remind you, what we did was to start with the relative and central mass coordinates. And what we showed was that the linear momentum, the total linear momentum, is a conserved quantity. We can rewrite the equation of motion like this, and the second derivative of the center of mass motion, which is the same as the acceleration in that frame, which again is a derivative of the central mass force, is equal to 0, which means that the total linear momentum is a conserved quantity. And we could then rewrite the equation of motion in the relative coordinates in terms of this equation here. And this is the equation which we can actually solve analytically. But in order to get there, we need to go through some technicalities. So I'm going to dive into the whiteboard, and we will stay there for quite some time. And I'm going to step you through the different ingredients which are needed in order to find the analytical solution. And then we are going to have the harmonic oscillator as one of the examples where we apply the theory which we are developing here. So let's switch to the whiteboard and go through these different technicalities. Some of these things are perhaps not the most exciting ones. I actually thought they were pretty exciting because it is one of these cases where you do actually have analytical solutions of complicated problems. So let's do that one. Now, a quick reminder of what we had on Monday. So we have a differential equation, since we transformed to the relative and central mass motion. So we have an R1 minus R2. And then we have the total central mass position, which is the mass of object 1 times its position, plus mass of object 2 times its position, divided by the total mass. M is the total mass. And then what we found is that we had the equation of motion for the central mass, the second derivative. So this is the acceleration for the central mass. We found that one to be 0, which means that we just have a trivial equation to solve for these degrees of freedom. And then the other equation of motion which we have is in terms of the relative mass. So let me just quickly remind you of that one. So that was M1 multiplied with M2 divided by the total mass. And then we had the acceleration for the relative motion, which was equal to the force, which also depends on the vector. And in our case, this is given by minus gamma. And since we were looking at the gravitational force, this is given by an R divided by R cubed. So let me quickly remind you, R is given by the absolute value of R. And if we are in 3 dimensions, this is obviously x squared plus y squared plus z squared. In our case, R being the difference between, R1 and R2, So just a quick repeat of what we derived on Monday. That means that in this case, the absolute value is then given by x1 minus x2 squared plus y1 minus y2 squared. Sometimes I'm a little bit too in a rush here when I'm writing. Plus c1 minus c2 squared. And what we found as well is that the angular momentum is a constant of the motion, which means that this is equal to 0. And so it's conserved L. So we don't need to think of that differential equation either. So L is a constant of the motion. And if you now look at the equations which we have here, we started with a 6-dimensional problem. We have 2 objects in 3 dimensions each. So we would have 6 degrees of freedom, and we normally call that a 6-dimensional problem. And since this differential equation for the center of mass is equal to 0, that means that this is a trivial equation to solve, and we don't need to worry too much about that. And then, since now we have a differential equation for the relative motion, when the angular momentum is conserved, what that means is that we can actually now position ourselves in just the xy plane. So since angular momentum is conserved, and we know that angular momentum is given by r times p, we can now redefine the x, y, and z coordinates. So we can redefine r and p to span the xy plane. And since the cross product between 2 vectors gives us a vector which is perpendicular to the plane, which is spanned by the position, the relative position, and the momentum, then we can simply say that we choose now the z-axis to be the axis where the angular momentum lives. And since this is a constant, nothing happens along the z-axis. And that allows us to take away that degree of freedom. So what we can do then is simply now to, when we redefine the coordinates so that the r and p live in the xy plane, then the z-axis is defined by L. And normally we would then say that this is LZ. And this is a constant. So nothing happens in that axis. So we can actually, the consequence of this is that we can then just reduce a 6-dimensional problem to a 2-dimensional one. So we actually have 2 dimensions, which are x and y. And what you will see now is that it's handier to solve the equations in polar coordinates. So we are going to make a transformation from Cartesian coordinates to polar coordinates. And we can actually solve the equation of motion in that coordinate system. We cannot solve the equation of motion in the XY system or the Cartesian system, because then we would not be able to separate the differential equations. And that's the big trick here. So that means that we are going to redefine the coordinates. So we define R to live between 0 and infinity. And then we have an angle phi, which now lives between 0 and 2 pi. And since we are on the plane, what this simply means is that we have something like this. We have x and y, and then we have the vector r, and we have it has its absolute value, which is r, the absolute value of r. And then we have an angle phi here, which means that x, in this specific case, is equal to r times cosine phi. And then y has to be r times sine of phi. So what follows now are just some manipulations where we are now going to rewrite this differential equation which we have, this mu times r, the second derivative, which is equal to minus gamma times r. So gamma is just a constant divided by r squared, r cubed, sorry. So we are going to rewrite that in two equations. One, which is going to depend on only the absolute value of r. And we are going to get an additional equation where we have d phi dt, which is equal to something. And these are two equations which we can actually solve analytically. And that's the strength of making this transformation. And you will often see that in physics. So like when you're going to take a course in quantum mechanics, you will see the same kind of trick when you're looking at the hydrogen atom, which is one of these systems which can actually be solved analytically. And then instead of solving the equations in the x, y, and z coordinates, the Cartesian coordinate system, you would make a mapping to spherical coordinates, and then suddenly you can separate the differential equations. And when you can separate them, so they don't depend on each other's degrees of freedom, then that is a very, very nice hint that you may actually be able to solve equations analytically. If you cannot separate them, if there are some kind of dependencies, and if you look at the equations for in the Cartesian coordinate system, there you will have a dependence on x and y in the differential equations for x and y. So you cannot separate them. And that means often, or normally, that you cannot find an analytical solution. Any questions so far? So this is just a kind of repetition of what we did on Monday. And now we need to actually get into the kind of small manipulations. So one of the things you see is that we would actually have to rewrite the derivative of x and y in terms of r, the magnitude. And we need also an equation for phi as a derivative with respect to time. So let's see how we can get these equations. So it's not too exciting, but this is a kind of tricks which you will often see in many, many different physics courses. So one of the things we need now is to look at the equation for r. So we know that the derivative, the time derivative of r, has obviously an x component and a y component. So we need that one first. So we started with an equation which looks like this. So we have a vector here, this one. So let's now skip the vector signs, just to avoid some complications with the equations. So I'm going to skip the vector signs, but we could just, if we keep the vector signs here, what we need now is the derivative with respect to x and the derivative with respect to y in terms of delta dt here. So let's now skip the vector signs, unless this causes some misunderstanding. Now, one of the things we know is obviously that when we look at r, so this is now given by x squared plus y squared. So when I take dr dt now, what I end up with then is obviously I have to take the derivative with respect to x. So that means that I get dx dt. Then I have in addition the derivative of the square root. So that gives me 1 over the square root. So I get a 1 divided by r. And this is also multiplied now with the derivative with respect to x, which gives 2 times x. But then I have 1 divided by the square root, multiplied with 2. So that means that the factor of 2 disappears. And then I get a similar one for y. So this is my dy dt. And then I have 1 over r multiplied with y. So if I want to have vectors here, then the only thing I need to do is actually to add the unit vectors in the x direction and in the y direction. So I'm just going to skip vector signs in the equations here, if that's okay with everybody, unless it creates some ambiguities. Then, if you look at this equation here, I can now calculate the second derivative with respect to time, because this is one of the equations we want to get hold of. And I can just take now the derivatives again of these equations. So that means that when I take the derivative with respect to time of this one, then I get the second derivative. And I'm just simply going to rewrite this as this, and then I have the second derivative with respect to x. And I take again the derivative of the square root. So that means I need also to keep track of this x times divided by r. I get an additional term. So this is just using the chain rule again and again of y divided by r. But then I need to take the derivative of the term which we have here, this term. So then I get dx dt squared. So again, I'm going to get a plus an x derivative squared plus a y derivative squared divided by r, because now I'm just using the derivatives of the denominator and the numerator. And this means that when I do it properly here, I get a final term which goes like r squared derivative divided by r here. So these are the equations which I get and which I now want to plug in to the differential equation. So this is one equation which we need. So let's frame that in, but we are not done yet, because we can actually simplify this equation here further. And we can simplify it further by looking at the expression for the velocity. So the velocity is going to be given by x dot squared plus y dot squared. So this is in the relative coordinates. And if we now look at the expression which we have for x, so we know that x is given by r times cosine phi, and y is r times sine phi. When we now take the derivative, the time derivative dx dt, and we use the chain rule again, what we get then is a d of r of cosine of dt, and this is multiplied with cosine of phi. But then I have to take the derivative of phi with respect to time, because phi depends also on time. So I get a minus, and then I have an r, and then I have a sine phi, and then I have to plug in a d phi dt. So this is again just applying the chain rule. Is everything okay? So it's not the most exciting thing we're doing, but we need to do this. And then I take the same with the dy dt. And this gives us simply a d of r of dt of sine of phi. And then I have plus, and then I have an r times a cosine phi times a d phi dt. And then I'm going to square these equations, because I'm going back to the velocity now. And if you look at the expression for the velocity, what I have are these equations squared. So that gives me now that an x dot squared plus a y dot squared. This is something which I can rewrite when I now square these equations. I'm going to get an r dot squared, and then I have a cosine squared. I get a plus an r squared, and I have a sine, and then a sine of phi. And this is now also multiplied with a phi dot squared, because I have a phi dot in here, the derivative with respect to time for phi. And then finally, I get a minus 2 times r derivative of cosine phi multiplied with sine of phi. And then finally have phi dot, or the derivative with respect to time. And when I take, sorry, this is x, or I can actually plug in everything here. So I can have an r, this is the y term. I have a sine of squared phi, and then I have a plus an r squared of cosine phi dot, not dot here, but phi squared. And finally, plus 2 times r dot cosine of phi times sine of phi multiplied with phi. And we see that there are two terms which cancel each other. So this term cancels this term. And if I now bring terms together, I'm going to have an r dot squared with a cosine and a sine. So that gives us 1. And similarly, I have this additional term here, which matches this term here. And that means I can rewrite everything here in terms of r dot squared plus r squared times phi dot squared. So this is my relation which I get for the velocity. And if we now go back to what we had, if you look back at the equation for the derivative, the second derivative with respect to time, what we can do next now is simply to replace this term here with what we have here, this term here. And if we do that, that last term, you will now see that this term here has a term which cancels exactly this one, which comes from the r squared dot here. But then we are simply left with this term which we have here. So when I then bring up the final expression for the second derivative, what I'm going to have now is a d of r of dt, the second derivative, which is equal to, and now I'm going to bring back the terms. So you have an x derivative, second derivative times x divided by r. And then I have the second derivative with respect to y multiplied with y times r. So let's just bring that in here. So we have x second derivative and then multiplied with x divided by r and plus y and y divided by r plus this term r squared and phi dot squared. But then I had an additional r here. So we have this r which you see comes from here. So it means that there is only the term which has an r here which survives. So this is the acceleration for the radial degrees of freedom, for the relative position. And now we are only looking at its absolute value, okay? So if you look at this expression here, if we now plug in that x is equal to r times cosine phi, and we use y is equal to r times sine phi, you see then that we can get rid of x here and r, and we just get a cosine phi, and similarly there. So we can rewrite this equation in terms of this x times cosine phi plus y second derivative times sine of phi plus this term which goes like r of phi squared. So if you now look at the two first terms, what is the first term proportional to? Any good suggestions? So you have an x second derivative. So the second derivative of position, what does that correspond to? It's this word which, yeah, that's the acceleration in the x direction. And then we have the acceleration in the y direction. And finally, we have a term which we haven't yet decided what it could be. So keep in mind now that what we have done is to rewrite the equations in terms of the relative position and the absolute value only. So there are no vectors anymore here. And then there's going to be a corresponding equation for the angle phi. So let's now take a closer look here at these equations. So we can now rewrite this. If I multiply with this relative mass, mu times d of r of dt. So there are no vectors here anymore. So this is mu times r second derivative. And this is mu times ax times cosine of phi plus mu times ay times sine of phi plus this r times phi times mu here. So the first term, which we have, this mu times a of x, this is actually the force, right? So this is the force in the x direction. If we now multiply this with cosine of phi, so what we have there is nothing but what defines the force in the x direction. And similarly, we would now have a force in the y direction. So what we end up with then is something which we can rewrite as a force in the x direction plus a force in the y direction plus r of phi times mu here. And I'm going to call this now for an f of r. So we just have a force which now depends on x and y only. There are no vectors now, times r multiplied with phi, second derivative squared, multiplied with this mass mu here. So this is actually the same as the acceleration in the r direction. So what we've done by these manipulations is to find out how the differential equation looks like when we now only take into account the absolute value of r. Now, this is something which we now can actually rewrite further. And there is going to be an exercise in the next week's homework. And we can actually show the following. So this d phi of dt of phi, and this is actually one of the exercises next week. So I'm just going to state the result here. This is the same as the angular momentum. So if you now calculate the angular momentum, which is r cross p, position cross product with the momentum, and you write it out in these polar coordinates, you will actually be able to show that this equation here is now given by the angular momentum divided by mu over r squared. So that means that I can actually rewrite my equation. So this is an equation which we're going to derive in the homework next week. So this is homework 8. So what we have now is an equation, if I now look at mu times r, which is given by this force in the r direction, plus the angular momentum, L squared. But now I have this to the power of 4. So I get L to the power, it should be, sorry, it's not L squared, but it's just L here. So we get L squared, and we have the 1r already. So that means I get mu times r cubed. And this is a differential equation which we have to solve. And this is the equation which we have an analytical solution to when we now plug in the gravitational force. Now, before we do that, there are some interesting things now which we can look at. So one of the things is that this term, which you see now, this L squared term, that does not come from the potential. So remember now that the f of r is the same as the potential and the derivative of that one and the negative derivative with respect to r. And in our case, this is the same as minus d of r, and then I have minus gamma divided by r. So if I do that, what I'm going to get now is minus gamma divided by r squared. So remember now that I have no vectors here. I'm just looking at the differential equations in the r and the phi direction. So this is the gravitational force which we plugged in, or something which looks like the gravitational force when we define the constant gamma to be the gravitational constant times the masses. However, the second term doesn't have anything to do with the potential energy. but it looks like an effective potential. This second term, which we have, this L squared, if you look into that one, this term here, this one, this comes from the kinetic energy only. Kinetic energy term. So this leads now to the definition of something we are going to call an effective potential, since we now have made a transformation from Cartesian degrees of freedom to polar degrees of freedom. So that means that the potential which we are looking at in the differential equation, that changes form. So let me try to explain to you what actually happens when you make this transformation. So you can actually, if you look at what you have here, you can define this as an effective force which contains an angular momentum plus the derivative of the potential with respect to the spatial degrees of freedom. So let me try to write this down and try to visualize the differences, because what we end up with is going to be an equation in R only, which we can solve easily. If we were to solve the equations with X and Y and Z in addition, we would not be able to decouple the equation in this nice way as we do here. Remember now that L squared is a constant. And you see now that the differential equation for R does not depend on angles. It depends only on R. So the equation which you have up here, the second derivative, this hints now at the possibility of finding an analytical solution when you do not have a dependency on other variables. Because angular momentum, we showed that that is a constant of the motion. So that means that L squared is just a constant. And then we have a dependence on R cubed here, but no XY dependence explicit in the equations. So let's try to look at it and see if we can gain some deeper insights, because this is going to lead to a way to interpret the data and what kind of motion we can expect. So if we now look at this, if we rewrite it, so we have mu times R, and we are going to call this for an effective force of R. There are no vectors now because we have reduced the equations only to the radial degrees of freedom and its absolute value. And then we have a minus dV of d of R plus this term which comes only from the kinetic energy. So this term here is only kinetic energy. And you can see that because if we go back to the expression we have for the kinetic energy, if you look at this one, this is if we multiply with the mass and divide by 2, this is nothing but the kinetic energy in the X and the Y degrees of freedom. And in that case, we had a term which goes like this R dot squared, but then we have this additional term here, which now is a term which enters the differential equation for the radial position. So we end up with something which comes from the kinetic energy, and we can now define everything which we have here as the derivative of an effective potential, V of F of R, divided derivative with respect to R. So this means that the effective potential has, in our case, to be equal to the original potential which we have. That's the standard gravitational potential. But then we take and integrate up this quantity here as a function of R. And then we just leave out the constants because everything is scaled with respect to some kind of level. And that means that what we get now is a term which, when we integrate up, which goes like L squared divided by 2 times mu multiplied with R squared. If you take the derivative of that one in the negative, you will get back the term which we had in the equation for the force. Now, what does this mean? This allows us now to make an interpretation of the potential energy when we now look at R as degrees of freedom, as degree of freedom. So we have R here, and then we can plot the standard Coulomb or gravitational force, which is given by minus gamma divided by R. So this is our original potential. If we plot this with X and Y, we would then have to put in, would have to make a three-dimensional plot with X and Y and the value of the potential. The next thing which we have is this term, which is called a centrifugal barrier, which is this L squared divided by 2 times mu times R squared. This is now going to be our effective potential, V of F of R. And then we add the two terms, we are going to get something which looks like this. So this is the V effective. And it's from that potential where we now are going to look at different types of equation of motion. So when we are at the bottom here, that is going to correspond to circular motion. And one of the things you're going to see then is that the acceleration in the direction of R is going to be equal to 0, which means at the bottom there, you move with constant velocity. So if you move with constant velocity in 2 dimensions, then the orbit is going to be a circle, because the radius of the orbit is the absolute value of the velocity, and that is constant. So that means that you have a circular motion. And the only thing which changes is the angle. And we're going to see that when we look now at the specific examples. Then, if you place yourself in other places in the potential well, suppose you place yourself here, that's going to represent elliptical motion. You can have parabolic motion, and you can have hyperbolic motion. So these are the type of degrees of freedom which we now are going to explore. But keep in mind that what we have done, we have made a transformation to polar coordinates. And in polar coordinates, we don't have exactly the same expression as we had in the Cartesian system. And we get an additional term to the potential from the kinetic energy. And this effective field or effective force which you get is normally called as centrifugal force. And we are going to see that this is actually the same as the centrifugal force, which are used for circular motion. So let's continue a little bit and make a small link between this type of equation and the example of the harmonic oscillator. However, what I wanted to state, and this is something which we will show in more detail on Monday, so we can actually solve analytically the equation of motion. So on Monday next week, so this will be 27th. What we're going to show then is that the solution to that equation, so we're going to have an equation of motion where I now divide by mu. So we have an R dot, which is equal to minus gamma divided by mu and 1 over R squared, plus this term now L squared divided by mu squared and R cubed. This equation here has an analytical solution, and the analytical solution is, we are going to introduce a new trick. We're going to rewrite things in terms of a new variable, 1 over R, which we call label for U. And this differential equation is now going to be rewritten in terms of an equation for du of d phi. And then we take the second derivative. So we replace, instead of having an equation with respect to time, we are going to have an equation with respect to this variable phi. And this differential equation is going to be equal to, in our case, a term which goes like minus u plus mu times this parameter gamma divided by L squared. So this is the equation which we're going to solve at the end. And this equation has an analytical solution. So mu is 1 over r. And it has an analytical solution which is going to be given by a times cosine of phi minus delta. So on Monday next week, we are going to show that. Today, however, what I wanted to show you is how we can interpret these results in terms of a two-dimensional harmonic oscillator. So before we dive into more tricks, because I guess you're pretty fed up of that now, we are going to look at an example, which is the harmonic oscillator in 2 dimensions. And that hopefully gives a little bit more insight in terms of these effective potentials. So let's do that, because that's a little bit simpler than jumping into the full equation for the gravitational force. But again, as I said on Monday, we are going to show that we can solve these equations analytically. And that's extremely useful. And then it's going to lead to elliptical orbits, circular orbits, parabolic and hyperbolic orbits, depending on the energy of the objects. And that's pretty neat. But let's look at the harmonic oscillator first in 2 dimensions. So what we have now are the following equations which we found. So we have an equation for phi, so which is d phi dt, and that's given by the constant mu divided by r squared. So L is a constant of the motion. And in addition, we have mu times r, the second derivative, which is equal to f of r. We will leave it unspecified, plus L divided by mu divided by r cubed. And now we're going to take the harmonic oscillator in 2 dimensions. So this is a harmonic oscillator in 2 dim. For that specific case, what we have is that the potential V of x of y is now given in terms of 1/2. And then we have this term k. And then we have xy squared plus y squared. And this is the same as 1/2 times k multiplied with r squared. So for the harmonic oscillator, you're going to see now that rewriting the equations in this way is actually stupid. So the harmonic oscillator is separable in x and y. So there is no point in doing this transformation in 2 dimensions. And you will actually see that this is a case where going from Cartesian coordinates to polar coordinates actually complicates life. So it's not given that if you make a transformation, you get something which is smarter and easier to solve. Actually, the harmonic oscillator in Cartesian coordinate is already separable in x and y. So we can solve the equation separately. However, this is actually a nice exercise because we are going to get the same type of effective potential from the kinetic energy. And this allows us to actually solve the harmonic oscillator problem in the radial degrees of freedom only, this quantity r, which is now x squared plus y squared. So let's take a look at that. And let's also see why solving these equations is in polar coordinates is not very smart. So when I rewrite the equations in polar coordinates, the equations which I have are these equations here. And the only thing I need to plug in is the harmonic oscillator potential. And we know that f of r in that case is simply minus dv dr, which in our case can be rewritten in terms of an x component and y component. But in this case, this is actually given by minus k times r. And in our case, we can also rewrite this f of x of y. This is going to be given, if we now think in terms of vectors, as a gradient of the potential in terms of x and y, which in this case is going to be given by minus k times x, and then we have the unit vector in the y direction, minus k times the unit vector in the y direction. Then what we have, when we look at the differential equations, what we are interested in is a dv dx dt. And that is given by the force in the x direction, which in our case is nothing but minus k times x. I have a dv, dy, dt, and that's the force in the y direction, multiplied with the mass here, or mu. And this is going to be given minus k times y. And finally, I also have the differential equation for dx dt, which is v of x, and dy dt, which is equal to v of y. So in this case, we actually have two equations in x and y, which do not depend on each other. And you can see that because the equation in the x direction has no y dependence, because the force in the x direction is simply minus k times x. There is no y dependence there. And we can then find the solutions here immediately, as we did before in the previous weeks. So we would find that x is now equal to a times cosine, and then we have this natural frequency times t plus b times sine of omega times t. And this omega is given by, is now given by k divided by mu. And similarly, we have y, which is given by a new constant times cosine. And then depending on the initial conditions, we can then find the solutions here. So in this case, if we now transform the equations to polar coordinates, we're actually not gaining anything. However, we can gain some insights in terms of these effective potentials. So let's take a quick look at that. So if we now go back to the harmonic oscillator in 2D with R and phi, what we have then is the following equation, minus mu times R second derivative, which is now equal to the force with this degrees of freedom plus L squared divided by mu over R cubed. And finally, I also have the differential equation for the angle, which is L squared divided by mu over R squared. And this equation here is actually an equation which is much more difficult to solve analytically than when we did this in the x and y degrees of freedom. However, there are some small insights which we can get and which we are going to transfer to the studies of the gravitational problem. So let's take a look at this kind of smaller insights which we can get by looking at this specific problem here. So we have a mu, so there is no advantage, let's state that, no advantage in transforming to R and phi from x and y. And that's because the equation for the harmonic oscillator is already separable in x and y. So in this case, we would rather use x and y. Now, let us now make an analysis, however, since we now have this machinery with the transformations, we can show that angular momentum is conserved because we have an energy conserving force, an angular momentum conserving force. So we have now an effective potential, which is going to contain the harmonic oscillator potential, k of r squared. And then I have my centrifugal energy, which comes from the kinetic energy when I did the rewriting. And then I can now ask myself, where is the minimum of this effective potential? Of d of r equal to 0. And I can then find that k of r minus L squared divided by mu over r cubed. If you want that to be 0, that gives an r min, and it's actually minimum because the function is convex. This gives an r min, which is given by L squared divided by this constant k times mu to the power of 1 over 4. So when I now plug in here, and this is the last thing I'm going to do. This is where we have our min for the harmonic oscillator. So it's a little bit different from a standard harmonic oscillator. And the thing we are going to see here is that the second derivative at R min, sorry, and this is the last thing I'm going to do today, because we will show this on Monday, at R equal to R min, this is going to be exactly equal to 0, which means that velocity is a constant. And if velocity is a constant, we have circular motion in X and Y. So we will see that on Monday next week. So this leads to circular motion at the minimum. And we are going to see exactly the same thing when we deal with a gravitational force. So these are the kind of small insights which we can get on the way in order to understand what kind of motion we can expect from these type of problems. So on Monday, I'm going to fill in these details, and then we move into the solution of the gravitational problem, and then try to interpret what kind of orbits we can get from that solution. So there's many small baby steps which we need to go through, but hopefully when you've gone through all these baby steps, you can see this beautiful summit, which hopefully gives many more new physics insights. So I'm sorry for going on along this tangent, but it takes us some time to get there. And sometimes we really have to climb and work hard to get to the summit. But when you are at the summit, hopefully you have a much broader view of what's going to happen. Okay, I'm going to stop here, but feel free to hang around and solve the exercises. As you know, we have there's nobody coming here after 4 o'clock. So if you wish to hang around and discuss the exercises, feel free to do that. If not, we see each other on Friday. Okay.